Very much. Okay, so I'll start with a quick summary of where we left off, which was kind of the summary of the first 3 lectures. So we were discussing quantum cohomology of quiver varieties and of affine-Grassmannian slices. And I had the same chart up last time. I just made a slight modification, which was to emphasize this duality at the top. So recall that for each symplectic resolution, we have 2 tori. One, which is the torus, which is acting on the variety, Hamiltonian torus acting on the variety. So in the case of quiver varieties, the torus acting is a maximal torus. You have this big group, which is the product of GL of all the framings, which is acting. And the torus we have acting is like the maximal torus of that big product of GLs. So I call it C star to the n. And remember this number, this n, which is always around, it's like when you write lambda as a sum of minuscules, it's how many things there are. So it's the same as the total dimension of the W's. And unless I'm mistaken, the diagonal C star inside that big C star to the n acts trivially. So it's really C star to the n mod C star. On the other hand, we have a second torus, which has played a lot of role in what we've talked about in the past few days, which is so-called Kähler torus. What's Kähler torus? So you take H2 of y with coefficients in C star. Dineker wrote the thing a little differently. You could say it's equivalently, it's the torus whose weight lattice is the Picard group. So the Picard group is always a free abelian group, a finite rank for a symplectic resolution. And it's the torus whose weight lattice is the Picard. And so that thing is called the Kähler torus. And why does it play a big role in what we've been doing? Because that's where this Q lives. So we had quantum multiplication, and the quantum multiplication depends on the parameter Q. And this Q lives in this Kähler torus. To be even more precise, Q doesn't live everywhere in the Kähler torus because there are these denominators here. So you want Q to not you want Q to the alpha to not be equal to 1 for all alpha which appear in this expression. So the alphas which appear in this expression are called the Kähler roots. And so the actual Q's here live in what I called before the regular part of this Kähler torus, the complement of this Q to the alpha equals 1. So for the quiver variety, this Kähler torus is identified with the maximal torus of the group G, whose Dynkin diagram we're working with. And that's basically because H2 of the quiver variety, you get one Z, one free generator for each vertex of your Dynkin diagram. Because the vertices of the Dynkin diagram gives you tautological vector bundles and tautological line bundles on your quiver variety. That leads to the Picard of the quiver variety, and that's why this is our Kähler torus in this case. Switching over to the affine-Grassmannian slice, there the torus is acting is this same torus, like the torus of G, which now is, for some reason, changed its name to T. But the maximal torus in G acts on the affine-Grassmannian and acts on every one of these affine-Grassmannian slices. So the acting torus is the torus inside of the group. And on the other hand, the Kähler torus, which is again defined as this H2 of y with coefficients in C star, again, it's related to H2, related to the Picard of the affine-Grassmannian slice. And as I explained, the Picard group, the line bundles on the affine-Grassmannian slice, they are pulled back from line bundles on the affine-Grassmannian. And this affine-Grassmannian slice, or more precisely, this resolved affine-Grassmannian slice, lives inside a product of n copies of the affine-Grassmannian. So you get n independent line bundles, which leads to this thing being C star to the n. Except there's this last line bundle, or the product of all the line bundles is trivial. So you have C star to the n mod C star. So I just thought I'd add that in. And as Dineker explained Tuesday in his exercise session, among the many things about symplectic duality is that these tori are swapped. And you can see that in the example. There's no, you might ask, what about the rest of the structure of quantum cohomology? What's swapped about it? There is a notion of equivariant roots, which I didn't get into, which is like the weights of the torus acting on the fixed points in the resolution. And those equivariant roots are swapped with Kähler roots under symplectic duality. We don't have an exact description of how the rest of quantum cohomology gets swapped, like what it matches on the dual side. The best we have is this thing called the quantum Hikita conjecture, which there was at least one poster about that. So something I developed with Michael McBreen and Nick Proudfoot, which is sort of like a kind of shadow of quantum cohomology, which you can see on the symplectic dual side. But I'm not going to talk about that. Any questions? OK, so now we're going to move on. OK, so all of this past few days was setting up this Okunkov formula and understanding this Okunkov formula. I just advertising your poster. You missed it. Setting up this Okunkov formula and understanding what this Okunkov formula amounts to in our situations of quiver variety and affine Grassmannian slice. So now that we've done the work and understood the quantum cohomology for these situations, you might ask, what should we do next? OK, so that's the next 2 lectures. OK, so let's start with our usual setup. We imagine we have a conical symplectic resolution, which of course you can imagine is either a quiver variety or affine Grassmannian slice. OK, so now I'm going to outline what's I call the, and I'm not the only one who called it this, the Bezrikavnikov-Okunkov program for studying this, for something interesting you can do once you. OK, so the first thing you're supposed to do is the following. So you're supposed to use this quantum multiplication by divisors. So that's exactly what we have so far. You're supposed to use this quantum multiplication by divisors in order to find a flat connection on a trivial vector bundle over this regular part of the Kähler torus. So the base of the vector bundle will be something I'll call M. So this M is going to be used a lot in what follows, so maybe just keep it in mind. So it's, by definition, it's this regular part of the Kähler torus, where Q lives for the quantum multiplication. And there's a way of using quantum multiplication by divisors to define a flat connection on a trivial vector bundle on this space. Trivial in the sense that it's isomorphic to the vector space across the base. And the fiber is the cohomology. OK? So this, I don't know if there's some physics motivation for building this connection this way, but certainly one motivation is you get back some natural connections. So for example, from the quiver variety, this yields something called the trigonometric Casimir connection. And from the affine Grassmannian slice, this yields the trigonometric Knizhik-Zamolodchikov connection. So like yesterday when I was saying, oh, there's all this work of Okunkov and collaborators to understand quantum multiplication by divisors, really, if you look at their papers, they're really about understanding this connection. So that's the main goal of all those works is to understand this connection. So I won't define this connection, but maybe you know exactly how to build the connection from this quantum multiplication. But in any case, it's not so important for our purposes. So I'm just outlining this program, but we're actually not really going to follow this program. I'm going to change the channel and go to a different program soon. OK. Once you have this connection, what do they say to do next? Well, if you have any kind of flat connection, always a flat connection gives you a representation of the fundamental group. In fact, there's a well-known equivalence of categories between vector bundles with flat connection and representations of the fundamental group. So from the flat connection, you take monodromy, and you get an action of the fundamental group of this base on one of the fibers. And the fiber is the cohomology of Y. And then you think, oh, what is this representation? So this brings you back to sort of classical results in representation theory about monodromy of this Knizhik-Zamolodchikov connection, monodromy of this Casimir connection, monodromy of the trigonometric versions, and so on. So that's the work of many people, but maybe especially Toledano Laredo has worked a lot on that. Now, what kind of group do we have here is the question you might ask. Well, what kind of space do we have this M? So let's take a particular M. So namely the M appearing for the affine Grassmannian slice is this M. It's C star to the N minus delta. Delta, remember, means that to the Zi equals Zj for some Ij. So this is n distinct points on C star. Modulo C star, not too important. So n distinct points on C star, the fundamental group of that space is actually the maybe pure affine braid group. So maybe you're more familiar with, you take Cn, the space of n distinct points in the complex plane, and you take the fundamental group of that, the points move around, and it makes you a braid. So this thing gives you, because it's like C star, instead of just a braid, you get something called the affine braid. And technically, I didn't, well, okay, anyway, let me not dwell on that. So you get an action of this interesting group, affine braid group, on the cohomology of the fiber. And you can try to, like the kind of game that these people do, is try to realize that action in a different way, coming from representation theory, say especially, say, from quantum groups and R matrices for quantum groups. So that's a kind of game in number 2. And then there's this game in number 3, which, I don't know, it's like a slightly surprising game. So you have this action of this affine braid group on the cohomology, coming from the monodromy of this quantum connection, which comes from quantum cohomology. And then there's this idea that maybe we should try to define an action. We should try to categorify this action. So this is an action of a braid group on cohomology. And one way to categorify cohomology is to think that cohomology is really the same as K-theory. And K-theory is a Grothendieck group of coherent sheaves. So then you can try to define an action of this affine braid group on a derived category of coherent sheaves. So each of these parts is like many, many papers of many different people. And so there's many ways of constructing such actions of affine braid groups. And I present 3, not even works, just general people that have worked on it. So of course, Roman Bezrukovnikov worked on this a lot using this idea of quantization in positive characteristic. Sabin Kadis, myself, and Tony Licata defined affine braid group actions using methods of categorical Lie algebra actions, and Daniel Halper and Leinster and others defined braid group actions in this kind of context using this thing called magic windows, which I don't know very much about. Okay.
In this case, y is also something it's an arbitrary representation, or is a...
Yeah. Y could be, I mean, whether you manage to do this or not for arbitrary symplectic resolution, we don't know. But you could try carry out this program for whatever favorite symplectic resolution you have. I'm not saying there's some theorem which says, like, for any symplectic resolution, each of these things works. Just something people did by hand in different cases, more like. Well, some of these methods are very general methods, like this Bezrukovnikov method. It's known that the symplectic resolution has quantizations. It's known that when you quantize in characteristic P, you have this big center. And this big center allows you to study the category coherent sheaves using modules in positive characteristic. And that kind of gives you a general method for constructing such actions. So there's some general methods here, not necessarily ad hoc. Any other questions? Yeah?
Is there an action which is like spherical twists or something like that?
In some cases, the action will be by spherical twist, but not always. Yeah, so like maybe most famous, I don't know, most famous. One famous example of this action is where y is a cotangent bundle of the Flag variety. There, the action is by spherical twists. Another famous case is where y is a resolution of AD singularity, and the action is by spherical twists. But in general, it's not necessarily by, I mean, even for the cotangent bundle of Flag variety, it's not by usual spherical twist, by some kind of like, I don't know what they call it, fibrid spherical twist. Any other questions? Yeah?
What is this connection for y cotangent to the flag?
So if y is the cotangent bundle of the Flag variety? Yeah, so that's a very well studied case. There's like there's papers about it, I guess, by Seidel and Thomas, and also by Bezrukovnikov, Riche. So that's a topic people have, I mean, I don't quite know how to answer your question. There is such an affine braid group action. There's many different ways of like studying it and thinking about it. I don't have the, yeah, it's off topic from what, I'm not going to try to get into exactly how it works, but it's a very well studied case. Any other question? Yeah?
To start with our trivial vector bundle.
Yeah.
Like we generally have a vector bundle with a flat connection gives you some number system.
Yeah.
But here, because it only treated as part, we get there is a particular kind of
I don't think so. I don't think so. Not that I'm aware of. Yeah. Okay. Anyway, so this was all what I called Vezdikov-Nikov approach, but now we're switching programs to Rybnikov program. And conveniently, Leonid Rybnikov just arrived here. So, okay, so here we are, new program. Okay. So, in this new plan, we have this M. So M was, again, where this open subset of the Kähler torus where the quantum parameter lives. So given any Q inside of M, we can consider all possible quantum multiplications by divisors. Okay, so this will be a subspace of the endomorphisms of the cohomology, right? I mean, every one of these quantum multiplications by divisor is an endomorphism of the cohomology. It's a subspace of the endomorphism algebra, and it's a subspace of commutative elements. Like all these elements commute with each other because quantum multiplication is commutative. And I call this subspace Q of Q. And so forming this subspace defines us a map from M to the space of commutative subspaces. And we can define M bar to be the closure of the image of M under this map. So you should think this left-hand side is some non-compact thing. It's an open subset of a torus. So it's kind of not compact in two ways. One, because of the infinities of the torus, and secondly, because we took out these hypersurfaces in the torus. So it's subtori of the torus. So it's kind of not compact in two ways. And we're going to compactify it by taking the closure of the image under this map. So this thing looks slightly weird. I mean, we don't usually, in algebraic geometry, necessarily study commutative subspace of endomorphisms of like what looks like an infinite dimensional vector space. But actually, you can make this far more concrete as follows. Well, first, let's just make things more finite dimensional. Let's just specialize the equivariant parameters. And let's call V just the subspace of all endomorphisms spanned by the classical multiplications and by those special operators L alpha. So this is now just some finite dimensional subspace, and one you can really get your hands on because we know what these guys are and we know what this is. And these quantum multiplications, because of that Okonkov formula, is expressed in this subspace. It is a linear combination of classical multiplications and those L alpha, those things called Steinberg operators. So M will be, this map here, Q goes to Q of Q, will be necessarily a map from M into a Grossmannian. Just an ordinary finite dimensional Grossmannian of subspaces of this vector space V. So here we have just, well, some non-compact algebraic variety, and of course here we have something compact. So we can take the image and take the closure. So that's a good definition of this M bar. Okay. So the first stage in this program is to define M bar and try to figure out what it is. We'll see some examples soon. Maybe very soon. Okay, well, I don't know why. Okay, maybe slightly out of order. Okay, we'll see examples of M bar soon. Second step, this was all about multiplication by divisors. For what comes, it might be more useful not just to have multiplication by divisors, but have all quantum multiplications. And this step 2 is maybe a little bit optional, but maybe you can prove that all quantum multiplications, not just by divisors, are well defined for Q in this M bar. Okay? And if you manage to do that, then you'll get an algebra, in fact, like a whole subalgebra, something bigger than this Q of Q. This is just some subspace. Here you get a whole subalgebra of this endomorphism ring. Of course, many times the cohomology will be generated by H2, so then this A of Q will simply be the subalgebra generated by Q of Q. That's not always the case. And other times, maybe this A of Q will be like the set of all things that commute with Q of Q. But in any case, sometimes, quite often, this Q of Q determines this A of Q. And okay, maybe before getting to that, let's just draw a quick picture here. Here's a picture. So this is supposed to be a picture of C star cubed minus delta mod C star. In what way is it a picture of that? Well, imagine you have a hexagon and you glue the opposite sides of your hexagon. You get a torus that way. It's not the usual picture of a torus, but it is a torus. And it's kind of like canonically what you would try to associate to S1 cubed mod S1, like that torus, or U1 if you prefer, maybe U1. So U1 cubed. So that's my picture of C star cubed mod C star. But then we had to throw away this delta. Delta was a locus where Q1 equals Q2 or Q2 equals Q3. So it turns out that one of these spaces, M bar, say in this example, will actually be a toric variety associated to this hexagon, where we also have blown up the origin. So it turns out we're going to, M is like the complement of all this stuff. It's kind of like this stuff. And then in compactifying it to M bar, we add two things. We add this divisor at infinity, and we also add back in these divisors, but then we also have to blow up at the origin. I'll explain a bit more about this procedure later, but I just wanted to draw you a little bit of a picture of what this M bar might look like. So M bar, you should think an open subset of a torus. M bar, you should think of a blow up of a toric variety. Okay. So step 3 is to study M bar. Actually, not all of M bar, but to find a nice real form of M bar. Okay. This step is maybe slightly harder to motivate, but let me just try to explain what we do. So we find a real form of M bar with a property that for everything in the real form, this algebra, A of Q, acts semi-simply with simple spectrum on the cohomology. So the algebra, A of Q, is acting on the cohomology. And if we choose this real form correctly, throughout the real form, the algebra will act by like Hermitian operators. So it'll act semi-simply, and hopefully it'll even act with simple spectrum. So all of the joint eigenlines for the action of the algebra will be all distinct. So it'll decompose our cohomology into one-dimensional eigenspaces. Again, we'll return to this point a little later. But once we do this, we can form a cover of this space. So somehow, in the first program, Bezrikov-Nikov and so on, the idea was to form a vector bundle with a flat connection. And now, instead of that, we're doing a kind of combinatorial approximation of that and forming a cover. Cover in the sense of topology, so just a finite, unramified covering of M bar R. Okay. Maybe I just threw in something in the corner here, also related to one of the posters in the poster session. There is this conjecture of McBrain-Proudfoot, which maybe is close to being theorem now, which says that you could study, rather than doing what we do, which is blow up this one and add some interesting stuff there, to not blow it up and just try to substitute Q equals 1 into this formula as best as you can. And the conjecture for McBrain-Proudfoot is when you do that, you'll arrive at the intersection homology. So I think it's very interesting to examine the relation between these approaches. Okay, next part of the story is that, okay, we have a cover. In topology, we learn there's a relation between covering spaces and actions of the fundamental group on sets. So we get an action of the fundamental group on the fibers of this cover, which is just a finite set. A finite set whose size is the same as the dimension of the cohomology, because it's just the eigenlines for this algebra acting on the cohomology. So we get an action of the fundamental group of this funny thing, M bar R, on the eigenlines of the cohomology. And this group, C, is very analogous to that affine braid group that appeared in the previous story. It turns out to be what's called an affine cactus group. So we'll get back to those affine cactus groups soon. I thought I had a picture. Okay, we'll get back to this affine cactus group soon. But there's going to be an action of this interesting group on this finite set. And then if you really want to try something analogous to the last step in the previous program, which was about some kind of categorification of that affine braid group action, you can try to think about some kind of categorification of this affine cactus group action. But I won't actually talk about this at all in these lectures, so I'll just put the words there and not talk about, not explain what's going on. But I'm just saying there is going to be some kind of analogous thing to categorification of this action. Okay. Any questions? So this all sounds a little like maybe abstract, but we'll see this in action now. Yeah?
So what do this eigenvalue correspond in the category?
Sorry, say that again?
What would be the object that correspond to this eigenvalue in category?
That's a good question. I don't know, but there'll be like some simple objects in certain hearts of this. So okay, this is getting a little bit out of hand, but there's this using this quantization positive characteristic. Bezirkov has defined these different T structures on the category of coherent sheaves. Unless you're familiar with it, you probably won't understand anything about this, but you're probably familiar with it. You may be familiar with it. And those T structures labeled by certain alcoves. And so the idea is that like those alcoves, in each alcove, the simple objects will be related to this eigenlines. And as you move from one alcove to the other alcove and the simple objects will change using this perverse equivalence, it'll match this action of this affine cactus group. Okay. Yeah? It's a good question. So let's just go back where M bar was defined. Here's a motivation or something. So we think of these different. We're thinking of quantum cohomology acting on cohomology. So for every quantum parameter Q, you have a different algebra acting on your cohomology. And as you're imagining moving this quantum parameter around and seeing how the action changes. But this parameter Q can only live in this open part of a torus. So now you're interested in what happens when the parameter Q goes to the boundary of the torus, or to the place where we took out those hyperplanes of the torus, and understanding what are all possible algebras that you get that way by varying the parameter Q. And M bar will be the space which parameterizes all possible algebras, which are also limits of quantum cohomology algebras. So sorry, just to continue, because this is like maybe the main point of what's going to come. So if M was parameterizing possible quantum cohomology algebras, because it's the parameter for quantum cohomology, now we're interested in seeing what happens when we, what are all possible limits of quantum cohomology algebras. Still what? Yeah, the dimension will be the same. I mean, we take the limit inside of the, depending on exactly your perspective about finding dimensional, but it depends which version of it, but like in this version, we're just taking the limit inside of this Grassmannian of k-dimensional subspaces of this vector space spanned by classical multiplications in the L alphas. So you definitely get something of the same dimension because you're taking a limit in that Grassmannian. Any other question? Sorry? That's true. Yeah. So there's like a, but then we're kind of going to introduce new pi1 by looking at this real locus somehow. So M bar might not have very much of a pi1, but once we look at its real locus, all of a sudden, again, it has an interesting pi1. Strangely enough. Like, right, so in the previous story was about staying in M and working with its pi1. Then we go to M bar, and it kind of gets rid of this braids because you can pass the braid kind of past each other. But then you do this funny real story, and you get back interesting pi1. I don't have a great explanation for why it works, but it does seem to work. Okay. Any questions about that? Things are about to get more concrete again. So this is like kind of a overview of where we're going in the next couple lectures.
EQ is same, is just the operator quantum multiplication
Yeah. AQ is the algebra of all quantum multiplications. For fixed Q, it's an algebra, which is all possible quantum multiplications acting at that parameter Q. Okay, so let's switch gears and things are going to get more concrete again. Okay, so for switching gears, I fix integer n. I introduce a finite dimensional vector space, which is going to be n choose 2-dimensional, and a basis labeled by elements Tij. And now, if I have n distinct complex numbers, let me introduce this Gaudin Hamiltonian. Well, I mentioned it before I put this omega ij thing at the top, but here I'm just, this Tij is just some fixed, some basis of this vector space Vn, a kind of abstract vector space. And I introduce these hi of z, which are these linear combinations of these Tijs. As follows, and I define g of z to be the span of those things. Okay, so this makes sense for z1, zn distinct. And of course, maybe not of course, but these h1 up to hn, they add up to 0. Well, it's not hard to see. If you add them all up, you'll get 0 because of some cancellation. So their span is n minus 1 dimensional. So this g of z is an n minus 1 dimensional subspace of this vector space Vn. It's supposed to be an n. Vn. And so we have an n minus 1 dimensional subspace of Vn. So we have a point in the Grassmannian. So this little paragraph here defined as a map from Cn minus delta, space of n distinct complex numbers, to this Grassmannian. Now, if we scale each of these complex numbers by some number, it will scale this difference, and so scale each of the hi of z's, but that won't change their span. If we add some number to each of these z1 up to zn, well, it won't make the difference will be the same, so hi of z will be the same, so it certainly won't change their span. So this map here factors through the quotient by simultaneous scaling and translation. So we have a map here. So again, we're in the situation. It's not completely clear at the moment, shouldn't be clear to you what this has to do with our question above, but it will have to do with it. We have a situation, we have this variety, which is a non-compact variety, embedded, it turns out this map's not hard to show as an inclusion, embedded inside this Grassmannian. So no problem, we can look at the image and take the closure. Anyone know the answer? Maybe you do. Here we go. So to explain what the answer is, first we do the following trick. We had n points, so we think of this Cn minus delta as n points in C, mod the automorphisms of C, which is, well, automorphisms by translation and scaling. We can add in a point at infinity and thereby obtain n plus 1 points on P1. So n plus 1 points on P1. They're still distinct, but now, like, because we added in a point, we should like take away the point or add something to the automorphism group. So we increase the automorphism group to be 3-dimensional PGL2. And you can go back, of course. If you have n plus 1 points on P1 modulo PGL2, you make one of the points be infinity using the PGL2 action. The rest of the points are in C, and the leftover group you have is the stabilizer of infinity in PGL2, which is this Borel subgroup of PGL2, translation and scaling. Okay, so this source space can be realized as n plus 1 points on P1 mod the action of PGL2. Or, and we'll call that thing mn plus 1. Equivalently, a curve with n plus 1 points where the curve is abstractly isomorphic to P1, but where you don't fix an isomorphism. So it's a moduli space of curve and n plus 1 points on the distinct points on the curve where the curve is abstractly isomorphic to P1. And this space has a famous compactification called the Lean-Mumford compactification. So we consider, rather than just a curve C, which is isomorphic to P1, we consider a stable nodal genus 0 curve, which is, so stable nodal genus 0 curve means it can have multiple components. Each component is a P1. All the components meet on nodes, and the graph of the components is a tree. And there's a n plus 1 distinct points on the curve, and this stable part means that there's no automorphisms, which means that every component has at least 3 special or marked points. And I don't know how you can see this over here. I like to think that these curves look a little like this cactus. I took this picture yesterday by the seaside. And so these guys, Aguirre, Felder, and Veslev, they were inspired by these cacti. Not really, but they proved this following great theorem, which is that the closure of the image of n plus 1 in this Grossmannian, that via the map I defined above, is precisely this Deligne-Mumford compactification. So I think this is a great theorem because a priori you get some, I don't know, some closure of like this mn plus 1. Why should it have to coincide with this closure you get from the theory of curves? There's no apparent reason why it should coincide with it, but it does. So this is one of my favorite theorems. Okay. Any question about all that?
So I guess there's some isomorphism between n0 and plus 1 bar with the closure of the.
That's what the theorem says.
Yeah.
Yeah. I mean, it's not just some isomorphism. I mean, you have mn plus 1 sitting inside of both things. So like it's the isomorphism is, there's no possible choice for the isomorphism because mn plus, like they have the same open subset. So there's isomorphism is unique.
There's a nice description of this isomorphism, like geometrically.
Yes, sort of. Let me, yeah, sort of. But it may be too complicated to go into it this one. Yeah. Any other question before I move on? Okay. So why is this like relevant for us? Okay, here's a huge chart. Okay, why is it relevant for us? So let's, where were we before? Well, let's start over here. So what's that? That's this regular part of the Kähler torus for an affine Grassmannian slice. H2 of this W lambda mu C star reg. And earlier, like at the first slide I showed you today, we saw that that was the same as this, right? It's this is the Kähler torus, so it has to do with line bundles on our affine Grassmannian slice, and there were n line bundles because we were in Grassmannian n, and then we took out the delta because of this regular thing, which meant that we took out the poles of all those q to the alphas, and alpha was epsilon I minus epsilon j. So that's why we have this. Okay. Now we do the same trick we did a few minutes ago. Here we have c star to the n mod c star. So we do the same trick. We add a new point, and we add another automorphism. So for the same reason, like you have n points on c star is the same as n plus 1 points on c, where you add in the point 0. I mean, we could also add in the point infinity, too. That's like sort of like the next step here. So here you add in 0. Maybe I should even do that right here. And here you can add in infinity. And here you have n distinct points on P1. And because the automorphisms are C star here they'll be PGL2, so we're exactly in this Mn plus 1. So this open subset of the Kähler torus, this parameter space for quantum cohomology algebras, is this Mn plus 2. Okay, now that's on the one hand. On the other hand, we explained a relation between, now on the other hand, we have this Vn plus 1. So Vn, what's Vn plus 1 again? It's that abstract vector space containing those basis vectors Tij. It's n plus 1 choose 2-dimensional. I mean, it was n choose 2-dimensional before, but I added plus 1, so now it's n plus 1 choose 2-dimensional. And it has an injective map to UG tensor n plus 1, mapping this Tij to that Casimir inserted at the Ij spot. We saw those guys, Casimir's inserted at Ij spot a couple of days ago. A couple of days ago we said this Casimir Ij spot, it can act on tensor products of n plus 1 dimensional representations, like this thing here. And we said that we have this isomorphism. This is what I call this Ginzburg-Riesz isomorphism between the inside here and the cohomology here. And we said that this guy acting here, transferred over to here, was exactly the term that appeared in that Akunkov formula for quantum multiplication. Okay, so this is also from the chart at the beginning of the class. And so because of all that, because of, well, which was Danilenko's work, because of all that, given this Q from here, if we map Q into the Grassmannian of n-dimensional subspaces of V, that should have been an n plus 1, Vn plus 1, by the construction that I just gave. So this thing is defined as those Gaudin Hamiltonian things, span of the Gaudin Hamiltonians. Then I map it here using this map here, I suppose. So that's this arrow here. I'll get exactly quantum multiplication by divisors. So I can, the upshot is, rather than studying so a priori I'm supposed to study the image, the closure of the image of that guy in here. And that's sort of harder to do. It's easier just to study the closure of the image of this inside a Grassmannian. And that's much easier because these guys already did it. So I'm happy. So as a corollary, corollary is the following. That indeed the compactified parameter space for quantum cohomology subspaces is the closure of the image of the map, i.e. the closure of the image of the map is Mn plus 1 bar. So using that Guerre-Felder-Veselov result combined with Danilenko and a little bit of this thinking, we can deduce this corollary right away.
So y is now, what is y? It's not arbitrary.
Y is not arbitrary, it's this affine Grassmannian slice. Yeah. So throughout this whole thing, y is any affine Grassmannian slice. Like notice the answer doesn't much depend on which slice it is. Just any affine Grassmannian slice with n plus 1, n with with lambda having n written as the sum of n fundamentals, n minuscules. So the answer is sort of universal. It hardly depends on the space. It's a bit weird.
And if I want to play with the pure varieties, it will be the same by some symplectic.
We'll come in there 1 second. Okay. Any question about this one? Okay. So what about for other symplectic resolutions? What's the analog of this corollary? For example, for quiver varieties. But maybe any question about this statement before I move on? Okay. Sorry. We'll get there in 1 second, but there's actually one more thing I want to say about this thing. This was all about, throughout this whole lectures, I've been kind of like a little bit going back and forth between saying just quantum multiplication by divisors and like all quantum multiplications. And like that's reflected here by saying what I call quantum cohomology subspaces. This is just like the subspace given by multiplication by divisors. Or I could talk about quantum cohomology algebras, all of the quantum multiplications. So the problem is, I'll make the statement here. So this is basically a theorem of Elin, myself, and Rybnikov. So we proved that actually a bit more is true, that this Mn plus 1 plus 2 bar thing is not just this parameter space for those multiplication by divisors, but actually for this entire thing called this trigonometric Gaudin algebras, which I didn't really explain what they are. If you remember the chart I had at the beginning today, there was a last line which was still conjectural. So assuming this conjectural last line, then it's the same as saying that this Mn plus 2 is the parameter space for all quantum cohomologies, for multiplication by all quantum, for all quantum multiplications, not just quantum multiplication by divisors. The point is, in principle, this parameter space could change when you pass from just this quadratic part to the whole thing, especially if it wasn't generated by the quadratic part. There could be, the compactification might get bigger, kind of, like it might surject onto the previous compactification. You might get a different, more stuff might get blown up. But we checked, for at least for these trigonometric Gaudin algebras, then you don't have more stuff blown up. Anyway, maybe it's not such a huge deal because I haven't been enough specific enough. Okay, let's go to those quiver varieties or other symplectic resolutions. So let me just recall again the perspective. We have some quiver variety. We already know, when I say quiver variety, I'm always in this finite AD type quiver variety. I don't quite know what the right the statements might be even more interesting in non-AD type quiver variety. But let's say AD type quiver variety. Already there, it's kind of more complicated. For AD quiver variety, we have our parameter space. This open part of the Kähler torus is identified with what I call H-reg, which is the regular part of the Cartan subgroup of our group whose Dynkin diagram is the quiver variety. So regular part means that all the roots don't have value 1. And we know that we get a map from that to the endomorphism of the cohomology, and Q is mapped to this all possible quantum multiplication by divisors, and we, thanks to Mollico-Kunkov, we have a formula for these quantum multiplications. So we know quite a bit here. But nonetheless, it's still a little hard to prove this kind of thing. So, okay, so here's what's known. Okay, so here's a theorem in progress due to Elin and Rybnikov in the case of quiver varieties, and somewhat related results due to Jeremy Peters, who gave a talk yesterday about this, in the case of hypertoric varieties. And the theorem says that what do you get? You get something called the Diconcini-Gaifi compactification of H-reg. So what is that? Well, I'm just going to import my picture from before again. So here's my picture of my torus. So H-reg means I took away these hyperplanes. Here's my, so without the hyperplanes, I just have, maybe I should, let's a little bit more, let's say it's here. So this stuff is H-reg. Then we compactify H-reg by a two-step process. First, we compactify it to a toric variety. And what toric variety is it? Well, in this quiver variety case, it's just the toric variety corresponding to the fan of the Weil chambers. So just like what's sometimes called permutahedral toric variety, at least in type A. I don't know what other people call it in other types, but I'll call it permutahedral toric varieties. So this toric variety corresponding to the permutahedron, you could say. So that's the first step, is to compactify to the toric variety. And then the second step is you have all those, you have all these subtori sitting inside of your torus, and therefore they're closures sitting inside of the toric variety, and you blow up certain intersections of these subtori. According to, well, this procedure is basically a modification of this Diconcini-Procesi wonderful compactification to this toric case, and it was studied by Diconcini and Gaifi. So we follow this procedure, and you produce what I'll call H-reg bar, so the result of doing this blobs. And so this theorem is, let's say in progress, that this is the description of the closure of the image of this map from the Kähler torus, regular part of the Kähler torus. Yeah, just one more comment before. If we started with this, maybe I'll just put it here. So if the G, like the Dynkin diagram we start with is the SLM Dynkin diagram, or maybe I just say SLN Dynkin diagram, so enough. If it's the SLN Dynkin diagram, so this H, in that case, H-reg is just C star to the N minus delta mod C star. And it turns out that this H-reg bar happens to coincide with this Mn plus 2 bar in that case. So in some sense, the previous story was like a kind of special case of this one. Although it's not literally a special case because it applies to more varieties than the ones that this theorem applies to. Question?
So in the case of, instead of considering a finite AD quiver variety, I would like to consider a fine AD quiver variety. Is there a fine version of the Concini-Gaifi compactification and conjectural the same should hold, or you're looking at?
I'll look at Lenya. He asked what happens for affine quiver variety. Quiver variety of affine.
Affine quiver.
Yeah.
Well, it does. So then there should be infinitely many subdomains. So this closure is not well defined as an algebraic scheme, but you can approximate it by something.
Work in progress.
Looking forward.
I mean, the problem is that I guess there's going to be infinitely many roots, right? So we have to remove all the roots, hyperplanes, so we're going to have infinitely many roots. So we have to, for example, in the case of the Hilbert scheme or something, you have to remove like infinitely points from C or something. Yeah. Anyway, theorem in progress. Any other question?
I don't understand how does this, like, what is the dependence on Q? In the sense that if Molly over cohomology is true, then you have some factor of Q, and then you have something which is in the standard variety, which is independent of Q, right?
Yeah.
So then the only way it depends on Q is just scaling, basically.
Well,
It's kind of equivalent to understanding this.
You mean, go back to this. Yeah, I mean, if we look at this formula here, you're right, Q enters here, but it doesn't give, I mean, it shows you when something bad will happen, right? Like something bad will happen when Q to alpha is 1. But just from this formula alone, it's hard to understand what the compactification will be. Like, it's hard to understand exactly what you'll need to do to fix the problem, sort of. Like, what does it mean that you've managed to fix the problem by going to the blow-up? It means you like multiply through by something, clear the denominators, and so on, and something that you do that's just something well-defined in the blow-up. But it's like not super obvious that that's like what you should do. Like, for example, even in this situation, you know, once again, when Zi equals Zj, we have a problem. But it's not super obvious why this going to this Deligne-Mumford compactification fixes the problem. So there's some work to be done to prove it. And usually the way this kind of theorems are proven is by starting with some kind of cover, like open cover of the space, and just like by hand kind of using these charts on the space, constructing this extension.
But equivalently, one can also just try to construct some compactified operators which somehow remove this problem. Like you can try to define some operators which can be defined on these bad values.
Yeah, well, that's basically the usual idea. So you define you work on like a chart in a neighborhood of one of these bad points on this compactified space, and on that neighborhood you define some operators, which makes sense. Basically by clearing the denominators in the right way, yeah.
In the first slide, the conjecture, for example, in the case, I don't know if this case is easier or not.
Which conjecture, sorry?
The conjecture on the first slide, go to the first slide, the summary, is a conjecture of the n, no? At least
Oh, yeah.
So for example, if I consider a schizo points on C2, would be easier to understand if all of this works and the rest, or would be complicated as a finite D case? You're looking again.
Look at linear again. But I think I don't know off the top of my head. Hilbert's scheme of points on C2.
It's easier to understand.
Do we know this fact, that the quantum cohomology algebra is the image of a beta algebra? Or something like that?
I think the Hilbert scheme is the most difficult case. Because it is not a Young identification algebra, right?
Yeah. So we don't even.
More like W algebra.
Yeah. So not known. Okay. Good thing that Lenya came just in time. Okay. I only have a couple of minutes.
No, you have 6.
Yeah, okay. 6 minutes. Where were we? Okay, back here. Okay. Okay, so now, so we're leaving behind this theorem in progress. We're going back to the case of affine Grassmannian slices. So in affine Grassmannian slices, we understand the space very well. The parameter space is this mn plus 2 bar. That was this previous theorem. So we're going back to this theorem. We have a good parameter space. So now what this general program is supposed to do is we're supposed to build this cover of this space and study this monodromy. I forgot if I maybe I didn't really say this, but maybe I say something in words. Let's go back to here, all the way back to here. Yeah, I did write it. I just didn't say it out loud. Okay, so this is what we're going to do now. Where this M bar is going to be this Deligne-Mumford space if genus 0 occurs with n plus 1 marked points. And we're going to try build this real form, blah, blah, blah. So why should, I wanted to just briefly explain a tiny bit why this should be like a reasonable thing to do. And this like a little bit summarized right here, okay? So just look at this thing I circled here. So what happens at q equals 0? So q equals 0 means we got rid of all the, well, q equals 0 is pretty straightforward. There's no problem setting q to be 0 because it just kills that term with the quantum multiplications. So you just get back classical multiplication. And what are the eigenvectors for classical multiplication? Remember, this is classical multiplication in equivariant cohomology. So if you multiply in equivariant cohomology by anything, the classes of fixed points will be eigenvectors. Because multiplying by the class of a fixed point is the same as taking your cohomology class and like restricting it to the fixed point. And when you take a cohomology class restricting the fixed point, you'll get a multiple of the fixed point, where the coefficient is something in the equivariant cohomology of a point. So, and because we've already localized equivariant, we've like, okay, anyway. So for that reason, multiplication by, for classical multiplication in cohomology, the eigenvectors will be the classes of fixed points. So over here at q equals 0, we have a nice eigenbasis given by the classes of fixed points. And so now we're going to like modify it and try to find eigenbases for our algebras at all these, well, other points in the moduli space. So I think that might give us slight motivation. Although it's a slight lie what I'm saying, but this might give us slight motivation for what happens. By the way, you might ask, what are these other, like, you know, our quiver variety has some other special points, right? These other t invariant points. What do they correspond to? According, I don't know if this is a theorem or not, but at least according to this Konkav kind of philosophy, these other points, they should correspond to other possible symplectic resolutions of our symplectic singularity. So we had the underlying symplectic singularity x. It may have multiple symplectic resolutions. Each of those symplectic resolutions could have some cohomology ring, and those other these other guys are supposed to correspond to those other cohomology rings. I mean, in many cases, maybe they're all isomorphic, but maybe sometimes they're not isomorphic. I forgot what they call this thing, large Kähler limit or something like that. Anyway, probably some people are more experts about this than me. Okay, so I think maybe I stop here, and then we'll, next time we're going to switch gears somehow again slightly, and we're going to discuss about this cover and so on. Questions?